Okay, so what we do here today is I want to talk to you about Java bytecode, and I want to give you a short introduction into the basics of it, because as you will see in the next hour, it's a pretty simple concept, and it's something that is worth knowing as a Java developer. And this talk today, it's split into two talks. It's in practice, right? So I don't only want to talk about Java bytecode as such and what it is. I also want to show you a bit what you can do with knowing Java bytecode and with manipulating Java bytecode. We have an hour for that, and that should be enough time. In general, if you have questions on the way, just go ahead and ask, and I'll be happy to help you. If English isn't a language you're comfortable with, just ask in Russian. I'm sure someone in the room will be able to translate for you. Okay, so Java bytecode. You probably all heard of it, but let's do some Java 101 to get started with. You all probably work with one of these languages or multiple languages, like Java, I guess all of you have used, or Scala, Groovy, Clojure is another popular choice these days. So how do these languages get executed on a virtual machine? And the way a Java program runs in the real world is that all of these languages compile to so-called Java bytecode. Java bytecode is, so to speak, the common format, the language of the Java virtual machine. And all languages, Scala, Groovy, JRuby, they also have to be translated into this common format, the so-called class file format. And thanks to this intermediate format, one can run applications that are written in different languages and they can still interact natively. Right? So a Scala program and a Java program, once they're both compiled down to bytecode, can communicate, because essentially for the Java virtual machine, it is the same sort of language. And that's pretty cool. Once you develop a language, you don't have to worry about as many things as when writing a compiler for machine code. You don't have to optimize a lot. You don't have to worry about the environment much, because the way a Java virtual machine is built is that at runtime you have so-called class loaders. You probably have discovered these once in your career, where a class file, which is basically just a binary array, gets loaded into the VM and is then interpreted or optimized and run by the just-in-time compiler. One other advantage, and maybe just to picture this is the first reason why today you want to know about bytecode. When you write a Java program and you write a Scala program and you want to connect these two programs, the language they communicate in is Java bytecode. This is the common interchange format, and if you want to debug something, you probably have at some point you have to look into how things are compiled, how the JVM actually sees your code. However, even more useful thing you can exploit from knowing Java bytecode is the fact that the Java bytecode format is something that is very well defined and easy to tingle with. So there's libraries. I'm writing one of these libraries. That's basically the reason I'm standing here today. I worked a lot with bytecode, and Byte Buddy is a framework for me that I wrote to make that easier. You can create such bytecode at runtime, and you can also read bytecode at runtime. And since you can write libraries that get executed by the Java virtual machine, you can see that there's like a circle closing in here, right? So you can write a Java program that at runtime manipulates itself to do something different. And that's often referred to as meta-programming or aspect-oriented programming, and that's the practical part that we want to have a look at in the course of this talk. Alright, but before we do that, let's just look at what Java bytecode actually is. And I like doing that by learning by example. So what I want to do with you in the next maybe half an hour is I want to compile some Java programs with you. And here on the left side we have source code. That's something you probably are familiar with, hopefully you're familiar with. And then we just want to translate it. So the first thing we look at is the easiest possible Java method. The Java method that doesn't do anything, it's empty. And if we look at the Java bytecode for this method, we will first recognize that it is not empty. Java bytecode is a list of instructions to the Java virtual machine, what it should execute. And any empty method will at least have one instruction, which in this case is the return statement. And you probably know that you can put the return statement also into the Java method. And that's something you have to recognize for the first time when you look at Java bytecode. Java bytecode is more explicit. Java bytecode is a machine language for the Java virtual machine. So it's supposed to be some form of yeah, it's less implicit, right? And the reason it is Java bytecode, is called Java bytecode, is that the instruction listings aren't represented by words but by single bytes. So the return statement is just the byte B1. So if you compile a method without any code inside of it, and you open the generated class file with an hex editor, you will find the byte B1. And that's basically how programs are represented to a Java virtual machine. You have to think about this as in a historical context as well. If you think about what Java intentionally tried to be, it was the language of the web. We had applets, we had small programs that should go on the wire, right? And the idea was to create a format that is as small as possible. So you have mnemonics like the return statement, but they are compacted. They are basically, the Java compiler tries to make things as small as possible, while the actual execution and the optimization is done at runtime by the just-in-time compiler. So this is the first starting point. So, but let's look at something more different. Let's add the numbers 1 and 2. The Java virtual machine, when it processes bytecode, it functions as a so-called stack machine. And the stack machine, you might remember from university, operates by having a stack where you can push values onto and pop values off. So if you want to add the numbers 1 and 2 in Java bytecode, it will look like the following. We have now 3 instructions which are executed in a sequence, and every instruction interacts with the so-called operand stack. So in this case, if we run this program, we will first execute the instruction iconst1, which pops the value 1 onto the stack. Then we have the same for the value 2. And now we have created a stack with 2 values on top of it. So the iadd construction, which we execute now, can pop both values off the stack and push it back on. Again, the reason that a stack machine was chosen for the JVM was that stack languages are really small. As a stack instruction always implicitly refers to the top of a stack without requiring a register address. Like my machine, for example, is x86. It requires register based instructions, but an advantage again is the size of it. And that's something important to realize when you think about a Java program, a compiled Java program. The abstraction doesn't not necessarily reflect the actual hardware. JVMs are virtual machines. They execute programs as long as they are correct. They are allowed to do whatever they want with the original program and optimize it. So this is really just a metaphor. The JVM, the compiled Java bytecode, is just a metaphor to communicate your intentions to the execution engine of the VM. We're not done yet. We have 3 on the stack, but we need to return it here, right? So this time we have to not use the return statement, which we already looked at, and it didn't do anything but return from a method. Instead, we have the so-called iReturn statement, and I indicates the type of the value that the method returns, in this case an integer. So what iReturn does, it pops the top value off the stack again, and it returns it to the caller of the method. Okay, so far so good. This is basically how the JVM works. Everything it executes is pushed onto the stack, and it's popped from there in order to process the values that we want to work with. Again, this is the bytes that you will find if you compile a class file with this method inside of it. You will find a sequence of these 4 bytes somewhere in the class file once you open it in hex editor. Okay, but let's look at another number, right? If we saw there's iconst1, iconst2, it's bytecode, so there's 256 byte values. How can we represent any number? And that's the next concept I want to introduce. Bytecode instructions can have parameters, and in this case the value 11 will be represented by an instruction called bypush, which takes an argument which is the actual number. The reason we have iconst0 and iconst1 is of course that the numbers 1 and 0 are very common numbers. So the JVM engineers thought, okay, if they are so common, by introducing a particular bytecode instruction, we can save space again. We can make applets faster, right? And that was really the original intent. Today you don't necessarily need it anymore, but that is legacy. That's a lot of Java, the JVM is a lot of legacy, a lot of decisions that were really important and smart at the time, but maybe it doesn't make sense anymore today. However, the bypush instruction takes the value 11, and then when you execute it, we again end up with 11 on the operand stack. And the rest we've already seen. We know how we can push to, we know how we can add these numbers now, and return the value from the stack by executing the instruction. So how does this look in the class file that we will compile again? Well, bypush is just a byte 10. Once the JVM discovers the byte with the value 10, it will know, okay, now the next value here, 11, the B in binary and in hexadecimal will be the argument. I will push this number, and the rest we already seen. So now, when we compile this class file with this method, we will discover these bytes in the actual produced class file. Okay, let's go a little bit further. Let's look at adding 1 to an argument that we give to the instruction. So far I've only told you half of the truth. There's not only the operand stack. The JVM in a way is a weird hybrid. But the idea behind the JVM is, again, it's only virtual. The JVM doesn't have to execute it. The JVM even doesn't need to have a stack machine as a hardware. It just needs to execute the program to remain correct. So what the JVM has, it doesn't only have an operand stack, it also has some random access memory. And here we have an instruction that's called iload1. What does iload1 do? It loads a value from the local variable array onto the operand stack. In this case, the first value, Java 0 based, which is I in this case. In compiled Java code, every method that is non-static is basically treated as a static method with the this parameter as the first argument to this method. And this is why we have I at the index 1 here. So once we execute it, again we end up with I on the operand stack. Then we have the rest here that we've already seen. We can run the same scheme again with I const 1, with I add, with I return, and we have executed the code. This is basically how the Java language, or the JVM rather, is evolved by adding new opcodes. I think today we have about 50 opcodes that are still free, so 50 bytes that don't have a meaning to the JVM yet. And once you want to add a new language feature that is basically has to be implemented on the JVM level, you just add an opcode, and this opcode will interact with the operand stack. Okay, again, this will be the bytes, and those of you that are already familiar with the JVM knew that I told you not quite the truth before. This time you will discover these 4 byte instructions in the class file before the Java C compiler did a small optimization, because if numbers are constant, they will just be merged, right? Other than that, the Java C compiler doesn't do optimizations at all. That's why it's so easy to tinkle with bytecode. The compiled program is still pretty close to the original Java code, because optimizations are rather done by the just-in-time compiler at runtime. So the mapping between bytecode and Java source code is still pretty close. Okay, so long we've only seen at int values, integers, right? Let's look at long this time. And one thing that you need to realize about the JVM is that the JVM is pretty close to Java, the language, and this is also true for the type system. So if you look at a language like Clojure, like JavaScript running on Nashorn, all of these languages have to statically map anything they do to the Java type system, including primitives, including reference types and object classes. And this is really difficult for implementers of such languages. So how does this look? Let's have a long value here. Once we have a long value, the Java C compiler will create different instructions. In this case, all the instructions as their mnemonic names will be prefixed with a L character. And the L basically refers to 64-bit values. On the local variable array, which is random access, we will now have 3 values, because the long value is basically treated as a 32-bit value split into the initial and the continuation. So it basically covers 2 slots. The same, and that's why we basically also need a different argument to operate with long values. So when we push something on the operand stack, it will now also cover 2 stack frames. And also the value 1 will be typed explicitly as a long. So once we push the value into the operand stack, it will also cover 2 slots here. We can now add both values, so we pop 4 frames and we push back 2 to end up with I plus 1 on the operand stack. And then we can return it. If we look at the bytecode, this time we have 4 entirely different bytes in the compiled class file than before. The Java C compiler or any compiler for the JVM needs to make decisions for us. And ideally, I mentioned before that the just-in-time compiler at runtime is responsible for optimizing code. And ideally, you could just shove in any code, and the Java compiler would figure out the ideal mapping. It would, of course, choose the most efficient data type, but it's not entirely true. Optimizing code comes with a cost, and if the Java just-in-time compiler at runtime would be busy entirely with just optimizing code, it could never run the actual program because it would be too busy just analyzing, going through the code. So it's important still, if you're a language implementer, to basically try to communicate the intent of your application as closely as possible. And if you have time later, I'm giving a second talk today about just-in-time compilation, and that's where I'm going to have a look at all these sides of how code is actually optimized. So please feel free to join me later again. Okay. So, but what about shorts? The fun thing about shorts is that they don't exist at runtime. When we compile this program, the i+1 part, even though I is now indicated to be a short value, is the exact same bytecodes. The thing about the Java virtual machine is that it doesn't really treat data types less than 32 bits as anything else. It's just streamlined everything. So when you read, like when you go on Stack Overflow and you read, okay, optimizing your program, use smaller data types on the stack, like you iterate through some shorts instead of iterating through some integers, it doesn't really make a difference because this information is already lost at the compilation stage. So when we run this program, we just end up with i+1 on the stack again. The short casting here, however, does have an effect, but it just adds another instruction. And this is basically just applying a bit mask to cut off two big values, such that shorts will never be filling the entire 32 bits. We'll just basically reset the first 16 bits to make it fit into the defined range of the short data type. And once you do it, it still is treated as an integer. So we still do iReturn from the end of the method. We just return an integer as well. And if you want to mess around with your colleagues, for example, you can manipulate the bytecode to just remove the I2S instruction. The method that is supposed to return a short can then actually return a value that is too big. So that's of course unexpected. If you call a method, you expect a short, and it's of the value integer max, right? So it's really just a facade that Java, the programming language, creates for you, which isn't mapped in Java bytecode. And that's basically true. You can do many things in Java bytecode that aren't possible in the Java language. The Java bytecode format is basically trying to be richer, even though it still closely aligns to Java, the programming language. Okay, so this is what's happening. And those will be the bytecodes that you will find in your compiled class file. Okay, so far we only looked at instructions. I think you probably got the picture so far. There's a list of instructions. Every instruction is mapped to a single byte, which the Java virtual machine knows about, such that it knows how it's executed. But of course, methods in Java don't just float around in the void. All methods in Java need to be defined inside of a class, and all methods need to be inside of a method, all instructions. So how does this evolve? Well, we've seen at this method, we've seen the return statement here, but of course every method needs to have a signature. And in Java bytecode, a signature consists of 3 elements. The first element is the so-called modifier. And modifiers you have seen in the reflection API. Modifiers basically signify all the properties of a method. If a method is public, if it's static, if it's final, all of these modifiers will set a certain bit of the modifier to be 1 instead of 0, and that composes a 2-byte value, which we find there in front. And then we also have the name of the method and the so-called descriptor of the method, which indicates what types a method takes as parameters and what type it returns. In this case, we have an empty method, not an empty method, we have a method without parameters, so we have the empty braces, and then it returns void, which is just shortened by simply using the capital V as an indicator for void. Again, Java wants to be small. It should be sent over the wire, so you wouldn't want to print void for every time you use void. You just use a single character, and UTF-8, it does 8 bits, 1 byte, which is of course less than 4 byte, right? Okay, and what we also have to tell the Java class file, or include in the Java class file, because it's processed by the JVM, is the size of the operand stack. Here we never push any value on the operand stack, so we can have an operand stack of the size of 0, and then we have to tell it how big the local variable array is. This is a non-static method, so we still receive this as an implicit first parameter, but we have to put the numbers into the class file that we compile. That's really annoying once you want to manipulate bytecode, because you have to figure out if you add something, if the stack has to be bigger and everything, you have to update these values as well. So, but how is this represented in a binary file? Right. Okay. A modifier, it's numeric. Numeric values are trivial to represent in binary. You just put the explicit value there. However, names like foo, the method name, or the descriptor of the method, are more difficult to store. So what every Java class has is a so-called constant pool. And the constant pool collects all strings that are used inside of a class. So if we have a class here, package bar, it will have a constant pool that contains a list of UTF-8 values and among other things. And here we have basically a list with indices where it says, okay, at this first index we have foo, at the next we have the descriptor, or we have the name of the class. Then we will simply have pointers to this constant pool. And again, this is a decision made by the Java virtual machine implementers or the Java C compiler implementers to make Java class files as compact as possible. If you refer to the method foo several times, then you only have to store the values one single time in the constant pool, and then you can always refer to that. And the people that implemented Android, for example, they went even one step further. They said, okay, class files are still too big. We have mobile phones with limited capacities, so we'll create a constant pool for the entire application. That's why you have to you need a second processing step in Android. You mingle a bit with the bytecode first of all to make it easier to process at runtime, faster to process at runtime, and also to compact things together, like to have a common string pool for all the methods and classes that are included in an Android application. Okay, the return statement, we already know how it's represented, and again, two numeric values are trivial to translate into byte representation by just using the numeric value. So now we have seen an entire method. So of course the indices of a method will change, and you will additionally have some numbers representing, for example, the size of the instruction list. But other than that, you will have methods representing in class files similarly to what you see here. That's also like I mentioned that we have indices. Every method has basically a single 2-byte value saying how many instructions a method has. And that's why a Java method is limited in size. You cannot add more than 65,000 bytes per method or something. Of course, I hope you don't write methods that are so big, but it's a limitation. And especially when you want to manipulate code and when you use libraries that manipulate code, and as a spoiler, you all use libraries that manipulate bytecode. I'll show you later how. Even if you don't touch this limit, you might get there after the manipulation, because you have to insert new instructions, right? Okay, we've seen the descriptor of the method ending with void. And I also told you that the Java type system and the Java virtual machines type system aren't fully aligned. I told you that booleans, bytes, short characters, and ints are all treated as integers in the JVM. That is true for the execution engine, but it is not true for the way you have to refer to methods, right? Because you can overload foo. You can have a foo with a short and you can have a foo with an int. So once you refer to a method, you have to use a so-called descriptor type, while on the operand stack, the JVM uses the actual Java virtual machine type. And there's you have seen descriptors already. Once you execute something and you see a stack trace, you will be faced with the surface of what the class file format is, because the Java virtual machine doesn't know what Java the programming language actually is. It's not a concept that's known to the JVM. So when you debug something, when you investigate a stack trace, the signatures will be those of the compiled class file format, because everything else was not included in the class file. So when you see like a exception thrown from a method that returns a boolean, you will see a method description with a set value, for example. And the same goes for references. References are referred to by the so-called type descriptor, which is starting in L, then the fully disqualified name where the dots are replaced with slashes, and a semicolon in the end. This is just a small summary where you basically see. And you see some weird things. For example, in the Java bytecode format, longs are referred to as L, but longs were inserted later, right? And at that time, the L was already used as a JVM descriptor for types, so they had to use a different letter for the descriptor, which then was J. Again, this is how the language evolved. This is just something you're stuck with. But yeah, this is the thing. Also, I mentioned that the JVM doesn't treat smaller data types and integers any differently. That is not true for arrays on the heap. If you have a field, it won't make a difference if it's short or integer values typed, because it is erased more or less by the execution engines. For arrays, though, a short array can be stored more efficient than an integer array, so then it still makes sense. Boolean types, though, are not treated any different at all, even if they're arrays. Booleans and bytes are reduced to the same JVM data type, even for arrays. So keep that in mind. A background is that the JVM forbids word tiering, and there's no hardware architecture in the world that allows you to address single bits of information. And the Boolean is a single bit, right? You always have to address this entire byte, so that's the minimum amount you have to use for storing a value somewhere. Okay. We've seen how methods are represented now. Let's see how methods are invoked. And methods are invoked by invocation instructions, of course. We've seen the I+1 part here, right? Once we invoke a method, we have instructions for that, and one is invoke virtual. That's the most common form of invoking a method in Java. And you guys know that in virtual method invocation is the default. You can override all methods almost. Only private methods you cannot override, and final methods as an exception. But otherwise, basically, everything's invoked virtually. And here's the clue again. Java used to be very slow in the beginning because Java was interpreted, and then virtual methods were actually virtual at runtime as well. But the just-in-time compiler now figures out if methods really are virtual and will reduce virtual invocations at runtime to a static invocation, for example. And this is really, again, just a metaphor. Never think about Java bytecode in matters of performance. Just think about bytecode as a way of communicating a Java program to a runtime. So, invoke virtual, such as bypush from before, uses arguments to communicate what methods to invoke. And the invoke virtual, in this case, takes the class of the invoking method, the name of the invoking method, and the descriptor of the invoked methods as its 3 arguments. However, we saw already we supplied the value I+1 to the method, but we saw that the local variable array for the foo method takes this as another implicit argument. So we have to provide this value as well, which is simply a load. A referring to reference types and 0 referring to the index. So as I said before, non-static methods, compiled versions are more or less treated as static methods with this as an implicit additional argument. Okay, and then we can return. Of course, this method will recurse infinitively, but let's not think about it. We just want to compile it, and compilation works pretty well. So, if we execute this method, how would this look like? Well, we would push a load as this onto the operand stack, then 1 and I and 1. And now we can add the top 2 values. Stack language implicitly refers to the top of the stack, so there's no problem with this being on the bottom there. Now we have this and I+1 on the operand stack, such that we can now use invoke virtual, which pops these 2 argument types off the stack and pushes back the result of the invocation. That's how method invocations are basically inlined into the stack metaphor, and how it can interoperate with values that you have created. And then we can return the value. Of course, we won't get there because it will invoke infinitively and throw in stack overflow error at some point, but you get the idea, right? And again, this is the bytes for every instruction. The invoke virtual is B6 simply, and these values are just again integers stored in the constant pool. So if you have defined foo already, the value isn't duplicated, your class file shrinks in size thanks to this optimization. Okay, so let's talk a little bit about method invocation. We've just seen invoke virtual, and what I want to explain to you what Invokedynamic, you've probably heard of it, what Invokedynamic brought to the table. So invoke static is a way of invoking non-virtual methods. Static methods are obviously methods that have the static modifier, and they don't have to be dispatched virtually. And this fact is hinted to the JVM by saying, okay, don't look up a type hierarchy for this kind of method. We expect this to be dispatched non-virtually because it's static. We've seen the virtual instruction. Then there's two more. There's invoke special. And invoke special is basically the dumping ground for everything that is out of order, right? Invoking a constructor, for example, is done by invoke special because in the bytecode format, constructors are nothing but methods with a specific name. And again, you've seen that on your stack traces. Constructors are called init in angle braces, and static blocks are called clinit within angled braces, right? And you don't want to dispatch constructors virtually. Constructors aren't inherited, so you say to the JVM, you know what, just invoke this method without looking up any hierarchies. The same is true for invoking a superclass method. If you invoke a method with super, you don't want to go down the hierarchy again, you want to just invoke the specific method that's defined in the superclass. And private methods aren't inherited either, so those as well, and since Java 8 we also cover interface methods there. Originally, invoke static, the bytecode was called invoke non-virtual, but yeah, it's not really true to that. So they thought, okay, whatever, let's call it invoke special. Let's use it for anything that is not the typical case. Then also for legacy reasons, we have invoke interface, which is used when you invoke a method virtually on an interface type. So if you look at these bytecode instructions, you can tell that they all have the same list of arguments. They take a class, a method name, and a descriptor. And for Java, for compiling Java code into bytecode, that works really well because every method is inside a class. You know how it is defined, where it is defined, and how to look it up. However, for dynamic languages, that is not true. And if you look at the new instruction, which was added in Java 7, Invokedynamic, we have a different set of parameters. In this case, we take a name for a method, we take a descriptor of a method, but then as a last argument, we take a reference to a so-called bootstrap method. And the bootstrap method is a pure Java method that is executed at runtime, which is used to determine the class which defines the actual method that we want to invoke. So let's look at an example. Let's say we don't have a language construct in Java for Invokedynamic, sorry. So let's just signify it here with question marks. And question marks aren't so far off because what Invokedynamic call site really expresses is that I don't know what method we're gonna invoke. And if you invoke JavaScript, this is a pretty good assumption. You don't know what code is gonna be run once you call something. At least you cannot reason about it statically. You have to execute the program in order to know what target the JavaScript method will have. So what happens once we reach this question mark call site is that we invoke the bootstrap method. And the bootstrap method really is just a Java method. For lambda expressions, for example, it's called the lambda meta factory. And you can go into this method, you can set a breakpoint there, and you will see the breakpoint being triggered once you reach your first lambda expression in your program. What the bootstrap method now does is it returns a reference to a class and a method in this class. And this method will then be bound to the question mark site. So if the call site says, okay, we invoke this bar method of the specific type, then this method will basically be copy-pasted into the question mark call site, and the bootstrap method will disappear and never be invoked again in the future. And then it is, and basically you can emulate this as well using reflection, right? But the problem with reflection is that the JVM doesn't recognize reflection in the same way that it recognizes normal method dispatch. So programs eventually became slower, and that was a problem, and still is a problem in Java, and that JavaScript or JRuby are difficult to run in an environment that always expects static typing for everything. And Invokedynamic made this problem not go away, but it eased the problem a lot. Because let's say bar now calls cooks, right? And what the just-in-time compiler does at runtime, it analyzes your program and says like, okay, let's say cooks doesn't do anything, it doesn't have any side effects, and it doesn't return anything. So the just-in-time compiler will say, okay, that's quite inefficient to run then, so let's remove it. And as a result, you might just be able to remove bar, which just invokes cooks, and then transitionally doesn't do anything either. And that might allow you to not call foo at all. And of course, if you can basically save yourself of executing all that code, even though you don't have to, you save a lot of runtime, and that's way more efficient than doing it despite not having effect. And yeah, communicating the intent of your program more natively to your just-in-time compiler, of course, helps the just-in-time compiler to optimize your program, and that's a huge deal for applications like JavaScript code or Ruby code or Clojure code. Allows compiler writers to communicate more efficiently what the program they compile is actually doing. So yeah, this is short text. Okay, so we have 26 minutes left. I hope you got a basic understanding of what Java bytecode is. I am fully aware that we didn't cover the full specification, because then we could have a 4-day seminar here. But the thing is, Java bytecode is not difficult. You understand what the general idea is now. If you want to look up something, you just have to understand how well you're pushed and popped often from the stack, right? It's nothing more than that. Java bytecode is really easy. So let's do something practical with it now. Let's implement a framework. In this case, let's implement the framework that you probably have used in a way, of course a very simple version. Let's do something that is similar to Spring Security. I guess you all used it. Let's see how it works, how we would approach implementing it. Okay, we have these annotations and we have the security holder. The security holder is basically reflecting on what user is currently logged into our application. In this case, we say, okay, it's the anonymous user when we start up, but then we can set the value to indicate who is authenticated. Then we have the secured annotation that says, okay, this method must only be callable once that specific user is logged in. So you have a customer, he wants to have this button where he can empty the database, and you want to make sure that absolutely no accident can happen, that this method is triggered by some hacker or something who finds a bug in the application. So you want to secure the method itself. And you say, okay, only administrators, so only if user is set to admin, only then it is legitimate to delete everything, right? So how do you do that? Well, you don't want to implement that yourself normally. You want to use a framework, a library to do that for you. So the framework basically promises that you can secure any class, and it will at least give you a secured version or even alter the class to be secured. So how can we do that? Well, there's a big problem here once you think about how to implement that program, because this framework promises to basically secure any service, and even the services that it doesn't know. And we have two different artifacts. The library, Spring Security for example, is compiled independently of your program, and it cannot have a dependency on your program either, because you cannot ring Pivotal obviously and say, yeah guys, I have this new application, I need you to support my service, please update the framework. So there's no chance to statically tingle with the service, right? But at runtime, so Spring Security. But at runtime, Spring Security, or the security framework that we implement, and your custom user code will end up on the same class path, for example. And then they are linked dynamically, and also using reflection, for example, you can discover code you don't know during compilation. And that way you can basically start working with the user code. However, at runtime, we already have compiled everything down to bytecode. We don't even know what programming language something is written in. We only see the bytecode, and that's pretty good actually, because that's a standardized format. So how can we work with that? How can we make the service secured? Well, the easiest or the most straightforward way would just be to redefine the method that you implemented, right? You have implemented logic for delete everything, so the framework does only have to parse the class file, find all the methods, since we know how this is defined in the class file, and just add bytecode instructions in the beginning of a method that basically do the if throw statement here. So what we can do is we can check if the user holder is currently holding the value admin. If that is not the case, we throw an exception. As a result, the actual delete logic will never be triggered, right? And you can do that. You can either use build time instrumentation for that. You can have like a Maven plugin that goes through your code before you bundle it in an artifact. Or what I personally prefer is to use a Java agent, which is a standard Java API to transform classes before they get loaded. We're gonna look at that a little bit later if we have the time. Yeah, but we will. The more common way of instrumenting is, however, to use so-called Liskov substitution. Liskov substitution works by the general Java convention that a subclass is always usable where you can use the actual type. So if we create a secured service, we can just basically hand out the secured service everywhere in our application, and if we override all the methods, the original methods will never be called unless they go through our dispatching logic. So in this case we can just say, okay, we override delete everything, and then we do the check, and we only call the super method if the check succeeded, because otherwise we have thrown an exception and will never reach that part of the code. And this is how Spring works, that's how Hibernate works. All of these classes use subclassing in order to transfer your code. For example, Spring opens a transaction for you in the try-catch block, and closes the transaction in finally, right? Or it does the security logic similar to what we see here. It's of course a little bit overly primitive, what I show you here, but the base idea is what you see here, right? The same goes for Hibernate. Hibernate just overrides all your setters, and once you call a setter, it knows that it needs to set a dirty flag, right? And if you call a getter, it knows that it might have to load the lazily from your database. That's all the magic, right? It's simple overriding, but at runtime. And a lot of people don't like that, right? So this is black magic. This is not goes too far out of the standard ways, but this is something people use every day in all kinds of languages. Think about JavaScript, right? If I define a service in JavaScript and I would call the service in JavaScript somewhere, then you can just hand over any object, because we don't have types. The runtime doesn't care about it, right? But then we don't have types at all. We have duck typing, and JavaScript also hugely relies on that fact. Like if you write an app in React, right? How does React know to re-render your entire page, or what segments of the page? Well, it basically overrides all your methods, or replaces rather in JavaScript terminology, with its own versions where the original method is called, and then there's a hook at the end of the state transferal to re-render the page, right? So that's how calling one of your methods results in a re-rendering. It's because JavaScript, or the framework rather, installed all these hooks. So, but with JVM instrumentation, you can get both the best of both languages, right? You can have static typing, what is really helpful most of the time, and you can opt out of static typing once you need to, if you want to basically work with user codes that you don't know at compile time. Okay. So, and you can argue, isn't reflection what that is for? But the problem with reflection is, if you look at the signatures here, that you lose all your type information. Once I basically, if I implement a security framework, I could offer you to give me a reference of method, and I offer you a static interface saying, okay, invoke, where I also have something here, like object and arguments. But then the Java compiler couldn't check for you anymore if the argument types are fitting the method signature, because it's reflective, right? It's determined at runtime. With code instrumentation, you just can overlay user types without this, hiding them, right? So that's a huge advantage, right? So 18 minutes left, and this is the reason I travel around in the world. I wrote a framework which has become quite popular, I would argue. And recently, the last year, I see the download rates skyrocketing, and I want to show you today how you can use it and how you can write applications that use code instrumentation, but without you need to know bytecode, or anybody in your team. That's basically one reason people don't want to use instrumentation many times, is because it creates this huge scary part of your application where a junior developer cannot touch anything without breaking things tremendously. So you want to abstract these things away, and Byte Buddy is one way to do it. So if you can read this code and understand what it does, I'm happy. That's the intent. So Byte Buddy is using a domain-specific language which should be as easy to understand as possible. But let's walk through it. Well, so we have entry point, which is Byte Buddy instances, and then you can basically say, okay, I want a subclass object here. So you know all what that is. You do something extends object. In this case, Byte Buddy will choose a name for you, but you can also do that yourself. Okay. Then you can say, okay, I want to intercept any methods named toString, and for objects there's only one method toString, which is the simple toString method, right, without arguments. And then I want to intercept this method to return hello world as a fixed value here. And of course it's not very useful, but it's a hello world example, so it's a good starting point. And then we make this class and we load this class, and then we can get the loaded class. And this is where we already enter the Java reflection API. So this is something you guys have seen, right? And now we can just call new instance and toString, and you can assert that this actually returns hello world. So what Byte Buddy has done for you, it has created a new Java class which adds a single method named toString as an override method, where the method overrides the original method to just return the hello world value as it is. Okay, so this is not very useful, right? So let's evolve it a bit. Let's spice it a bit up. So again, we want to subclass object and intercept toString, but this time you want to use a so-called delegation. So you can just tell Byte Buddy to delegate an invocation to a specific interceptor. In this case, this is one that you wrote. In this case, it's really easy because you just say, okay, to this class, and what Byte Buddy will do then for you, it will figure out a best match. And since there's only one static method, it's pretty easy to find the best match. It's just the only method that exists. And again, we will return hello world, of course, but this time you can, for example, set a breakpoint. So you can debug better. And of course, you can compute a dynamic value. In there, you can return some random string, for example, every time. Then that's what the method will gonna do. So Byte Buddy will glue your interceptor code and the generated class together to do what you want, and you don't even have to know about bytecode. But it goes further. Of course, you want to have some context of the method you intercept. So for example, you want to know what method it is that you intercept, so you can use your interceptor for different methods and react accordingly. So you can tell, for example, to inject the method that is intercepted. In this case, it will just return here a reference to the toString method in the Java Reflection API format. So this method will just return hello world from toString. Yep. Okay, and one big, you might have looked at cglib or javasys and other libraries, and one big advantage with annotations is that annotations are treated as metadata by the runtime. So if they're not available on the class path at runtime, they will just be ignored. So it allows Byte Buddy to be used in OSGI environments, on application containers, wherever you might have such class path issues, which was actually one of the major reasons I started writing Byte Buddy in the first place. I was working on another open source project with some people, and we were just stuck. Our application, we thought it was really good, but people weren't using it that much because they couldn't run it on OSGI or all these containers. We had a huge problem with that using cglib back in the days. Okay, and Byte Buddy offers you an entire lot of annotations, so you can write all sorts of interceptors. You can basically do anything that you can do in Java. You can request all the values, and you can retain type safety as much as possible. Okay, but let's look at some other features of Byte Buddy before time runs out. So one thing you might have heard of, what Java virtual machines support, is a so-called hot swap feature. Hot swap feature allows you to change code at runtime. So instead of running the defined code, you want to run some different code. In this case, let's say you have defined a class foo with the method bar that just returns the string bar, and then you have created an instance of this class. So using hot swap, and Byte Buddy uses the hot swap feature internally, but offers a convenience API, you can still get what we shown before, but for an existing class at runtime. So after we create an instance, we can go in and say, okay, we want to redefine foo instead of subclass foo, and again we want to take the method bar and return hello world instead. And what we will then get, then we have to use a so-called class reloading strategy here, which uses the Java agent API. And what we then still get is that foo.bar will return hello world in your application. And that sounds not very useful, right, in the first place. And your colleagues will be very angry with you because that's not what they expect when they run their code. And you edit that, and that's what they get, right? But it turned out that I was only playing with this feature, and then I deployed it at some point. But people are using that a lot because people use third-party libraries. They use legacy libraries where they cannot make changes anymore, where they're not allowed to make changes, or where making changes is too difficult. Then sometimes you want to test code, and the application unfortunately hard-coded to call some external service, right? And you cannot get rid of that. So what you can do is you can just say redefine this third-party service, because it's already compiled, right? It's on the class path, it's all static. You can treat foreign code as if it was your own without you having to recompile anything. So what a lot of people do is they say, okay, this service, this method, just redefine it to not do anything, so I can run my unit test. And then at runtime and production, I of course don't do that. Also, some people mock out methods that would otherwise throw an exception. And of course that's hacky, but if I'm working as a consultant, all applications I've seen in my life are really hacky at some point in life, and that can help. So I do that myself. Okay, so, and one limitation, unfortunately, is that you cannot add new methods. So you have to make sure that you don't also something you do with Byte Buddy, that you, for example, override a method of a superclass that's adding a new method to the actual class, right? That's not allowed. The instrumentation API will throw an exception for that, but there's a JEP 159. I really hope it gets merged someday, and that might let us do more complex things with that. And there's a prototype called the Dynamic Code Evolution Java Virtual Machine. I've work on another project called Mockito, and I have great plans once this JEP is there, because then you can do all sort of things, mocking final methods, all that. So that would be awesome. So I hope it comes out and then this API is ready. Okay, so how can we, however, get the benefits of what I showed you already today? One API that you might have heard of but never used, or maybe have used but in pain, is the Java Agent API. And Java agents are basically programs that are run before the actual Java application. And they allow you to install so-called class file transformers. And class file transformers obviously allow you to transform class files, and that is at the exact time that this class is or some class is loaded, among other things. So Java agents are broader, but I would say that's the most useful features about Java agents. So Java agent is the second box here, the second chart. It's an own artifact. You will put it onto, not on the class path, but you will put it on the command line. So you start up your application by saying Java, I don't know, minus class path or CP. Then you list all your chars, and you also add minus agent, and then you add this other char, not at class path, but at agent, right? And then it gets executed as an agent. A Java agent is supposed to define a single method, static method like main in a Java program, but this time it's called pre-main, because it's invoked before main, right? Makes sense, pre-main. It takes a single string argument. There's no list of arguments. You can only add one or 0, and then this will be null. And as a second argument, you get an instance of the so-called instrumentation interface. And the instrumentation interface is a very sharp tool which allows you to do very powerful things. You can extend the bootstrap class path, for example. You can compute the size of objects, the actual heap size, and it allows people to use hooks in two very internal processes, and one is class loading. Unfortunately, the API basically requires you to map one byte array to another byte array. That's the bytecode part that we've seen before. So basically you have to parse it, you have to look into where you want to add things, and then you have to generate a new byte array representing the transformed class that is returned from a method, and if you do anything wrong, the instrumentation will be swallowed silently. So what Byte Buddy does, it offers a so-called agent builder API, where you can say, I want to rebase, that's the terminology I use for that, I want to rebase classes. In this case, you want to rebase any class that is named foo without a package, right? This is the one we have up there. And then you can tell it to transform it. And the second part here, the builder part, that you have already seen. That's the same API as before. So you can reuse your subclassing instrumentation to also be applicable for Java agents. And then you just say, okay, I want to install it on this instrumentation, and the deal is done. If you run the above code, the foo class, with bar returning hello world instead of bar, that is possible. Again, I don't argue that's a very useful use case, but let's say you implement a security library, you can do that as a class path drop-in. The thing is, with subclass instrumentation that Spring uses, is that Spring needs to manage all your classes. You cannot use new anymore in your application, more or less. It all needs to be containerized, right? Because you don't want to have instances of the actual class that you wrote, but you want to have instances of the subclass that's only created at runtime, which you cannot refer to since it's only created at runtime. This way, you'd rather use your own classes, but you redefine them at runtime silently and invisible for the actual application code, and it will still work, and it will work for every instance that you ever create. So, like side effects, anything that is cross concern code, that you can really do neat things with it. And I get a lot of mail from people doing sometimes very ambitious things that might not be a good idea, but I've seen really cool things being done with this API already. So feel free to use it, of course. Yeah, I have some color here. So so far so good. This works really great for Java. We have no hacks. We don't have internal API calls, no sunmisc unsafe. We just use standard APIs. And this works because Java, as I showed you in the beginning, is a stack machine, which is rather easy to manipulate. So this is a nice side effect, even though it wasn't thought of maybe in the beginning. It's a really nice way to interact with code today. And this is just-in-time compiled, meaning that the format that is represented to you at runtime is bytecode. Bytecode, which has a very well-defined specification that you can work with, right? However, there's Android, and Android, for various reasons that of course make sense. Android runs on small devices, so they decided we want to have a register-based VM. And register-based VM is closer to the actual hardware, like my phone. It's I'm not sure what architecture it has, AMD something, I guess, which is register-based on the machine level. So you want to make the translation step easier. If it's already register-based, you can basically transform into machine code with less computational power. So it makes sense to only do this once at compilation time. You already pre-compile your program in a way. You still get bytecode, and it's still just-in-time compiled, but the bytecode format that Android uses is much more complex. And the class file format that Android uses is insanely complex because what I mentioned before, you have a single constant pool for the entire application. This constant pool is sorted by name of things. So if you want to add something, you basically have to rewrite all indexes in the entire application, which is ridiculous. And I had some experiments with saying, okay, you can only introduce new names into the application that start with 10 sets, right? But that's in a way, it wasn't really fun to try, and in the end I gave up. However, I support a subset. All the subclassing part you can do with Byte Buddy, even on Android. But the redefinition part isn't that interesting on Android anyways, because there's no instrumentation API. Android only implements a subset of the Java APIs. That's why there's so much arguing about if this is legitimate, because it's not a fully implemented Java virtual machine. Also, one reason that I gave up is that Android introduced a new runtime called Art, and again, it's a great runtime, no doubt about that. But it's still register-based, but now it's ahead of time compiled, basically forbidding you to do any bytecode manipulation, because at runtime you only have the machine code accessible anymore, which is of course again taking into account that Android applications are fired up quickly, have a short lifetime. You know, you go on your phone, you check Twitter, and you go to your browser and close Twitter. So there's not much time to do optimizations. There's not the same concept of a desktop app or server app that runs for a long time and has a lot of memory available. Android is simply, I mean, arguably, Java Virtual Machine isn't the perfect runtime for mobile device, but not necessarily even because phones get stronger. But it's something people have thought about and decided about, and that's what we have now, right? So, but as I said, I have a version of Byte Buddy that is runnable on Android, which is based on the official Android DEX compiler, so it works really neatly. Here's some numbers. That's benchmarks run with JMH, Java Micro Benchmarking Harness, that is coming with the OpenJDK project. Of course, micro benchmarks in Java are very difficult. Again, I can only invite you to join my second talk today. I'll talk a bit about that as well. But obviously, I wouldn't have this slide if Byte Buddy wouldn't be faster than the alternatives out of the market, and I would just silently drop this discussion. But since I wrote Byte Buddy 3 years ago, I started, and CGLib is out for soon 18 years. Of course, I could take into some advantages in the Java language and the JVM layer. And I use tools like Just-in-Time Watch, which actually allows you to look at machine code during runtime to see what the JVM likes and doesn't like. As I mentioned, the JVM doesn't always compile things efficiently if you do weird things, right? So that's me. You can follow me on Twitter if you're interested in code generation, instrumentation. That's basically my thing, right? I do performance, I do memory model. A lot of JVM internals is kind of I try to go this direction professionally, but it's also my hobby. If you want to look at Byte Buddy, please do, because it's a lot of work. If nobody uses it, I feel bad. So tell everybody, and I'm just one person, so I can only do so much evangelism. And also, if you want to look at, I have another open source project that's actually, it's not as known, but it's very widely used. It's a document converter for Java. It offers Java adapters for running like Microsoft Word or Microsoft Excel from Java without needing to worry about the processing model behind, such that you can do conversions like Word to PDF. It's online documents for j.com or on GitHub. And yeah, that's all for me. Thank you so much for coming. I don't know if you have time for questions. I run out for 1 hour. I don't want that Volker has to struggle. But maybe one or two, and then you can find me. I'm here all day, and have a talk later. Yeah.
Thank you for your presentation. I want to ask about sub-signature methods.
Sorry, what?
Sub-signatures methods.
Yeah.
How it looks in bytecode, and it is possible to understand that cases with Byte Buddy.
I wouldn't say that Byte Buddy is much of an exploration tool. The idea of Byte Buddy is that the entire bytecode abstraction, the entire internal abstraction, is hidden from you. That goes up to currently I'm working with hiding generics from you, because currently Byte Buddy deals with erasures, but hopefully I can release it that year. I want to basically give you the impression that you're in an IDE. When you describe something to Byte Buddy, it's the same. It should be the same image that it displays, that IntelliJ or Eclipse will display to you. So, is that what you were asking?
Okay, I ask you later.
Yeah. Okay. No, fair enough. Any other questions? Yes?
So, quick question about Mockito, because you're a contributor and you're doing Byte Buddy as well. So, is it possible to use? Would it be possible to have a Mockito mocking a final and static method before this GAP lands using, say, Java agents? Is it something that's possible?
That's something that's absolutely possible. That's something we look into. The problem is that people are very hesitant to use Java agents, and the problem is not the JVM. It's not how we could implement it. It's the tooling. Java agents is not supported by unit testing framework so well. It's difficult to isolate when you run tests. You would have to update plugins, because plugins just allow to put things on the class path. So for us, ideally, if I could make a wish, you could just call or have something in your module descriptor or in your jar descriptor that says this is actually an agent, so that you don't have a specific thing anymore. Of course, that's a security threat in the worst case, because I can just say, okay, whenever this method is called that goes to the database, I want to email all the database content to my account. So I understand why it's isolated a bit and made more explicit. But yes, this is actually exactly what we look at. This is how PowerMock works, just by creating different class loader hierarchies. But what I want to do with Mockito, at least it's my personal plan, to basically allow stripping final modifiers, to have inline mocks where you don't change the class, don't subclass, but you change the class to have like a flag. This is a mock. This is not a mock. And that's also, I mean, reading the Mockito mailing list, this is one of two questions that we get, like five questions on a week. So that's something people actually would use. So I hope we can get there at some point.
Thank you, Rafael.
Okay, I think we're done here now, but I'll be here for another talk, and I'll be around, right? If you want stickers, I have literally thousands at home, so I brought some of them. Please feel free to grab as many if you want, and thank you so much for coming.